In this video, we're going to be having a look at trigonometric ratios in a right-angled triangle. Now that's a long phrase, trigonometric ratios, so we'll talk about them just as trig ratios. What I've got here in this diagram is a straight line, and marked off are the points A1, A2 and A3. And each one of these is 10 centimetres on from the next one. So that's 10 centimetres, that's 10 centimetres, and that's 10 centimetres. And I've made a right-angled triangle by drawing vertically up from each of these points to meet this line here. So in effect, what I've got is an angle here at O, an angle here at O. And I'm extending the two arms of the angle like that. But the angle's staying the same. Even though the separation is getting bigger, the angle is staying the same. And what I want to have a look at is what's the ratio of that length to that length as we extend. So that length to that length, and then that one to the whole of that. I want to have a look at that and see what it actually does. So, I'm going to use a ruler, do some measurement, but these are fixed at 10 centimetres each. So first of all, let's have a look at A1, B1 divided by O, A1. Well, the bottom is definitely 10 centimetres. We've had that before. And if I measure this one with the ruler, it's 6.1 centimetres. So that's 0.61. Now let's have a look at the same ratio for this extended angle, this bigger triangle. So we'll take A2, B2 over OA2 equals, now this OA2 is 20 centimetres, so that's over 20, and take our ruler and we'll measure this, and that's about 12.2. 12.2. We do the division and we've got 0.61 again. This bottom one, just to check, is 30 centimetres long, so we want A3B3 over OA3, and that's 30 centimetres, we've just measured it, and if we measure again here, this is 18.2, so 18.2 centimetres, and if we do the division, that is 0.60, and it's going to be 6 recurring, which is about 0.61. So what we see is that all of these three ratios are the same. So if we take the side in a right-angled triangle which is opposite to an angle, and we divide it by the side which is adjacent to it, then opposite over adjacent seems to be constant for the given angle. And indeed it is. And we have a name for it. We call it the tangent of the angle. So, take a right-angled triangle, right angle there, and let's look at this angle here. I'll label it angle A, so we've got a clear picture that that's the angle we're talking about. Let's give names now to the sides. The longest side of a right-angled triangle, the one that's opposite to the right angle is always called the hypotenuse. So there we have the hypotenuse. Usually shorten it to HYP. This side is opposite this angle. It's across from it. It's opposite to it. And so we call that the opposite side, which we shorten to OPP. This side is a part of this angle, so it is adjacent to the angle. And we shorten this to ADJ. If I take not this angle but that angle, then some things change. Let's draw the diagram again. This time let's focus on the angle B. This side is still the longest side and is still opposite the right angle, so it is still the hypotenuse. But it's now this side which is opposite, across from the angle B. So this side is now the opposite side. It's now this side which is a part of the angle, which is alongside the angle, which is adjacent to the angle. So if we change the angle that we're talking about in a right angled triangle, we change the labels. They're not fixed until we have fixed upon the angle that we are talking about. Let's now take a little step back. Remember, at the beginning of the video, we said that if we picked our angle and we took the opposite side and the adjacent side, then the ratio of the opposite to the adjacent side was a constant, and that we called that the tangent of the angle A. Well, tangent's a long word, and we tend to shorten that simply to tan. What other ratios are there in this right-angled triangle? Let's label this side as the hypotenuse. And the other important ratios that we need to know about and be able to work with are the opposite over the hypotenuse, which is the sine of the angle A. And for all we say sine, we shorten it in written form to sin, S-I-N. We don't say that, we say sine. The third of the major trig ratios is the adjacent over the hypotenuse, and this is the cosine of the angle A. We shorten that to cos A. Now, all of these have been worked out in tables, and before calculators, mathematicians used to work these out quite regularly and publish books of tables of the sines, cosines and tangents of all the angles through from 0 up to 90 degrees. In doing all the calculations, things like a calculator are invaluable, and you really do need one to be able to work with. What we're going to have a look at now are some calculations, working out the sides and angles of triangles when given certain information about them. When doing this, it does help if you have a way of recalling or remembering these definitions. One of the ways is a nonsense word, soatoaka. Sine is opposite over hypotenuse, tangent is opposite over adjacent, and cosine is adjacent over hypotenuse. Soatoaka. Some people remember it as Sokotoa, simply changing the syllables around. Still means the same thing. Others remember it by a little verse, Tom's old aunt sat on him cursing at him. And again, tangent is opposite over adjacent, sine is opposite over hypotenuse, cosine is adjacent over hypotenuse. Whichever you learn to help you remember these ratios, that's up to you. But it is helpful to have one of them. So, let's have a look at some problems. Many of the examples that we want to look at actually come from the very practical area of surveying. The problem of finding out the size of something, the length of something, when you can't actually measure it. Typically, perhaps, the height of a tower. So, we're stood here, and we want to look at a tower over here. And how high is that tower? We can't measure it, we can't get to the top of it, but how can we find out how high it is? One of the ways is to take a sighting of the top of the tower. And with an instrument, surveying instrument, we can measure that angle to the horizontal there. So let's say we do make that measurement and we find that it's 32 degrees. We can also find how far away we were stood from the base of the tower. That's a relatively easy measurement to make as well. So let's say that was 5 metres. Somebody about 6 foot tall probably measures about 1.72 metres, there or thereabouts. So we're set up. We know how far away from the tower we stood. We know this angle, sometimes called the angle of elevation, of the top of the tower from our eye. So, how high is this? Well, here we've got a right-angled triangle, and we know one side and we know an angle. And this is the side we want to find. It's the side that is opposite to the angle. So let's label it as the opposite side. This side is 5 metres. It's the side that we know, and it's also adjacent to the angle. So what trig ratio links opposite and adjacent? Well, the answer to that is it's the tangent. So the opposite over the adjacent is the tan of 32 degrees. Right. We're in a position now to be able to solve this, to be able to substitute in values that we know and placeholders for those that we don't know. So the opposite side, let's call that x. And so that's x for the length of the opposite side over 5 metres is the length of the adjacent side. Equals tan 32. To find x, we multiply both sides by 5, so x is 5 times tan 32. And now this is where we need our calculator. 5 times tan 32 equals, and the answer we've got there is 3.124, and then some more decimal places after it. One word of warning, by the way. Most calculators operate with angles measured in one of two ways, degrees or radians. You need to make sure that your calculator is operating with the right measurement of the angle. I'm using degrees here, 32 degrees, so my calculator needs to be set up so as to operate in degrees. the answer to my question, how high is this tower, we haven't quite got yet. And the reason we haven't got it is we've only got this length here. And so the height of the tower we can find by adding on the height of our eye above ground level. And so that gives us 4.844 metres. This is a very accurate answer. It says that we know the height of this tower to, well, a millimetre. This place here is 4 millimetres. That's far too accurate. We would probably be happy to say this is 4.8 metres and work to two significant figures. Let's have a look at another example. Here we've got an equilateral triangle. Well, not equilateral, sorry. Let's make it isosceles. Isosceles triangle has two equal sides. And in this case, we'll say that we know this side is of length 10, and we know that this side is of length 12. And we'll have the units of measurement to be metres. Now, it's an isosceles triangle, and the question is, how big is that angle? There doesn't seem to be a right angle. In questions like this, you've got to look to introduce a right angle. And here, if we divide the isosceles triangle in half, down the middle, this is our right angle. And so here we've got a right angle triangle. And we know that if this is 10, then this is half of 10, 5 metres. Let's look at these sides and label them. This side is opposite the right angle. It's the longest side in the right angle triangle. So it is the hypotenuse. This side, which we also know, is alongside the angle. It's adjacent to the angle. Let's give this angle a label. Let's call it the angle A. What trig ratio of the angle A connects the adjacent side and the hypotenuse? Well, that's the cosine. So the cosine of A is equal to the adjacent over the hypotenuse. And we can substitute the numbers in. The adjacent is 5. The hypotenuse is 12. Now, I've got a problem here. It says cos A is equal to 5 over 12, and I want the angle A. The angle A is the angle whose cosine is 5 over 12. I've got a problem about how I might write that down. And to do it, I write it like this. Cos to the minus 1 of 5 over 12. And what that bit there, this cos to the minus 1, says is the angle whose cosine is. So let's put an arrow onto that and write that down. The angle whose cosine is. That's what this piece of notation means. And now I've got to work that out. So I need to look at my calculator. And we're looking for the angle whose cosine is, and we can see that as cos to the minus 1, which is just along the top of the cos button. And it's on the shift key, therefore, the second function key. So, in order to calculate it, we have to press shift, cosine key, and we see that we get cos to the minus 1, bracket, 5 divided by 12, close the bracket, and that gives us the angle of 65.3756, etc. degrees. and I'd probably give this to the nearest tenth of a degree. In other words, to 1 decimal place. Let's take another example. This time we'll take the isosceles triangle again. $15 meters for that side, and because it's an isosceles triangle with those two sides equal, that one will also be 15 meters. And we'll say that's 72 degrees. Question, how high is the triangle? Here is the height, and that's what we're after, the height of that triangle. So, let's label our sides. This side, the one we want to find, is across from the angle. It is opposite to the angle, and so it becomes the opposite side. This side here is opposite the right angle. It's the longest side in the right angled triangle, and so it's the hypotenuse. What trig ratio connects opposite and hypotenuse? The answer is sine. And so the opposite over the hypotenuse is equal to the sine of 72 degrees. H is the length of the opposite side, the height of the triangle we're trying to find, over the length of the hypotenuse, that's 15, is equal to sine 72 degrees. And so H is 15 times the sine of 72 degrees, multiplying both sides of this equation by 15. And again, we're now at a stage where we need our calculator, and so we want 15 times sine of 72. And the answer we have is 14.3. And here we work to 3 significant figures. Let's take one more example in this area. And the example that we'll take is where we're finding a side, but perhaps it's not the one that we might expect. So there's the right angle. Let's say that this angle up here is 35 degrees, and that this side is of length 6. And what we want to know is how long is the hypotenuse. This side is the hypotenuse because it's opposite the right angle. It's the longest side in the right angled triangle. This side that's of length 6, let's say 6 centimetres, since lengths have to have units with them, this is the adjacent side. It's adjacent to this angle. What's the trig ratio that we need that connects adjacent and hypotenuse? It's going to be the cosine. And so we have adjacent over hypotenuse is equal to the cosine of 35 degrees. The adjacent side is 6. Let's call the hypotenuse x. So 6 over x is equal to the cosine of 35 degrees. So 6 must be x times the cosine of 35 degrees, multiplying both sides of this equation by x. This sometimes gives people a little bit of trouble, the next step. We've got 6 equals x times cos 35, and it's the x that I want. The thing that you have to remember is cos 35 is just a number. It's just a number like 2 or 3. So if this said 6 was equal to 2x, then we'd know that x was equal to 3, because we'd be able to divide the 6 by 2. Cos 35 is no different, and so we divide both sides by cos of 35 degrees, and that will be equal to x. So we need the calculator again. We have 6 divided by the cosine of 35 degrees. And the answer we get for x there is 7.324. And if we shorten that to 3 significant figures, that's 7.32 centimetres to 3 significant figures. We've looked at some problems, and there are some more on the example sheet that accompanies the video. One of the things that we do need to have a look at, though, are some quite specific angles and their sines, cosines and tangents. And it's important that these are learned. Learned because they are exact, and because mathematicians, scientists, engineers use these a great deal in their work. The angles that we're talking about are the angles 0, 30, 45, 60 and 90. We're going to have a look at their sines, their cosines and their tangents. Let's have a look at a right-angled isosceles triangle to begin with. There is its right angle. Isosceles, each of these sides will be the same length. So if we use Pythagoras, 1 squared plus 1 squared is 1 plus 1, which gives us 2. So the length of the hypotenuse must be root 2. And each of these angles, because it's isosceles, are 45 degrees. So, from that triangle, can we read off the sine, cos and tan of 45 degrees? Let's concentrate on this angle. This is the angle we're going to concentrate on, that 45 degrees. The sine of 45 is opposite over hypotenuse. And so that's the opposite is 1 over the hypotenuse is root 2. So that is 1 over root 2. The cosine. The cosine is the adjacent over the hypotenuse. The adjacent is 1, the hypotenuse is root 2, and so the cosine is 1 over root 2. The tangent is the opposite over the adjacent. And so the opposite is 1 over the adjacent is 1. 1 divided by 1 is just 1. So we've completed that middle column of our table. Let's now take an equilateral triangle. All the sides are the same length, all 2 units long. And that means that all the angles will be the same as well. So they will all be 60 degrees. Haven't drawn in the top angle because I'm going to split my equilateral triangle in half. So each of these will be 30. And there is a right angle down there. I've split it in half, so each piece of this is 1 unit. So there are my angles, and all the lengths are marked, except that one, the height of this equilateral triangle. Let's work out how long that is. Pythagoras tells us that that squared plus that squared should give us that squared. Well, that squared is just 1, and that squared is 4. To add 1 to something and get 4, the answer has to be 3. So that means the length of this is root 3, the square root of 3. So now we can read off from this right-angled triangle sines, cosines and tangents for 30 and for 60. So let's look at 30. The sine is the opposite over the hypotenuse. The opposite is of length 1, the hypotenuse of length 2, so that is 1 over 2, a half. For the cosine is the adjacent over the hypotenuse, and so that is root 3 over 2. Root 3 over 2. For the tangent, that's the opposite over the adjacent, so that's 1 over root 3. Let's have a look at this one. 60. Starting with the sine. Sine is opposite over hypotenuse, so that is root 3 over 2. Cosine is the adjacent over the hypotenuse, so that is 1 over 2, a half. The tangent is the opposite over the adjacent, and so that's root 3 over 1, or just root 3. What about these bits, 0 and 90? Okay, let's take any right-angled triangle. And we'll fix on this angle. So that's the hypotenuse, that's the adjacent, and that's the opposite. Okay, sine is opposite over hypotenuse. If we imagine this angle going down towards 0 like that, it's clear that the opposite side is becoming 0 itself. And so we have 0, or a number approaching 0, being divided by the hypotenuse, which is pretty large. That would suggest that the sine of 0 is 0. But what about the cosine? As this comes down, the hypotenuse becomes almost the same length as the adjacent, which would suggest that the cosine of 0 is 1. And the tangent? Well, the tangent is the opposite over the adjacent, so as this side goes down, the opposite side becomes 0 over a fixed side, so again 0. What about 90? Let's imagine this angle begins to get bigger and bigger and bigger, so that it looks like it's going to become 90. And what we can see is that the opposite and the hypotenuse become almost the same, suggesting that the sine would be 1. But as that is happening, the adjacent is becoming 0, and the cosine is the adjacent over the hypotenuse. And so again, that goes to 0. Finally, the tangent. That adjacent side is becoming 0, becoming very, very small. But this opposite side is staying fixed. So we've got a fixed number, and we're dividing it by something which is getting very, very small. So the answer is becoming very, very big. In other words, it's becoming infinite. And we write that as an 8 on its side and call it infinity. So this is a table of sines, cosines and tangents that are all exact and for very specific angles. 0, 30, 45, 60 and 90. These need to be learned. They are important, and textbooks, scientists, engineers in their everyday working and everyday calculations take these as being read. They assume that they are known, and so you must learn them and make sure that you have them ready to hand to work with immediately. You hear sine 45, that's 1 over root 2. Tan 60, that's root 3.